Hi Mario, it's a classic game and let's do this. Because I love to make this a special video and hate sleep in a social life, I'm gonna be testing not one, not two, but three different AI algorithms. I'm talking the best of the best here. We got genetic algorithm, we got neural evolution of augmented topologies, and we got proximal policy optimization. Right now, we're watching 5,000 parallel games played by an AI as it travels through the famous and classic stages of Super Mario Bros. In the beginning, it starts with no knowledge whatsoever and was only capable of pressing random buttons. But throughout 1000 hours of simulated game time, it gains many capabilities by learning from its experiences. Eventually, the AI is able to jump over obstacles, find secret warp pipes, even weaponize Koopa to shell surf through waves of enemies, and finally defeat Bowser himself. I promise I will not end this video before the AI can defeat Bowser. But we are getting ahead of ourselves. Game first, AI later. Let's make Mario. Okay, player with the platform done. It's a square and a rectangle. Very nice. Creative work. Nice. Gravity. Done. Let's gravity. Boom. Let's go. Ground. No. Ground. No. This is getting annoying. Ground. Oh no. Oh yes. Yes. It's so easy. Just give me a challenge next time. Okay, so the ground is done and it's looking pretty good. It's nothing revolutionary, but it's a start. Okay, let's start with the player controller. It's a combination of scripts that allow us to control a character within our game. Press right to move right. Press left to move left. Hold B to jump and down to duck or warp into secret pipes. Okay, can it go right? Yes. Can it go left? Yes. Can it jump? Yeah. Yeah, well, close enough. Sideways jump and gravity and collision at the same time. Let's go. Everything is coming together. This must be what Steve Jobs must have felt like. It's just a square and a rectangular base. There are like couple of things that I like to add, but honestly not that much. We are pretty close. So the challenge right now is to accurately copy the movements of Mario from the official game. But before we do that, we need to understand the killer movements of Mario. Let's look at Mario's most basic move, his run. Mario's run can be split into three parts: acceleration, top speed, and deceleration. As in, once you start moving the stick, how long does it take the character to reach top speed, and how long does it take to stop when you let go? Getting these two curves right is the key to making Mario feel natural. Keep them short and your character feels stiff and robotic, like in Mega Man 11 and Celeste. Make them long and your character feels heavy and sluggish to set off, like in Super Meat Boy. In Super Mario Bros., Mario has long acceleration and deceleration curves. It takes him about 72 frames to get to full speed, which takes about 12 times more time than Madeline of Celeste the game. And he also comes to a stop in 72 frames, which takes about 5 times more time than Super Meat Boy. These long curves are exactly why Mario feels slippery, but also gives that satisfying sense of momentum and makes you really feel the weight and momentum of the character. Next, it's Mario's jump. First, we calculate the character's jump height by looking at how high they can jump compared to their body size. So in Super Mario Bros., Mario can jump to a point that's 5 times his height, while Meat Boy can massively jump high to about 6 times his own height. And there are two types of jump in Mario. First, short hops, just tap B, and second, long jumps. Just hold B and don't let go. The longer you hold, the higher you go. And then we look at each character's curve, noting the climb, hang time, and fall. For example, Meat Boy has a tall and a lengthy jump, making him feel floaty, while Madeline has a short jump. She goes up and down very fast, while Mario has the best of both worlds, having both long and short jumps. For short jumps, you just tap B. And for long jumps, just hold B and don't let go. The longer you hold, the higher you go. Here's the thing, building Mario from scratch takes time and I don't want our AI doing nothing while we are pixel pushing. So while we are busy recreating the game, we are gonna deploy a secret weapon, a classic NES emulator. Think of it as a hyper space-time chamber for our AI. We can harvest mountains of training data all without waiting for our game to be ready. Essentially, we are transforming the Mario console emulator into a local AI accelerator. Turns out OpenAI already cracked this problem. They built Gem Super Mario Brothers, a plug-and-play emulator where we can start training our AI right away. Meanwhile, I'll keep building my own version of Mario from scratch. Trust me, we are gonna need it for what comes next. Are you saying that you're gonna need your version of game for PPO and deep reinforcement learning? You will see. But for now, one quick pip install and we are logged in. You know what? It's time to implement. After some extensive research, I realized genetic algorithm was simple. Imagine this, I want to beat Mario. I make a working copy of Mario. I turn off the monitor and play completely black. Wait, what? So you are playing Mario, but your monitor is completely black. You cannot see the Goombas. You cannot see the pits. You cannot even see Mario. The only thing you know after each run is you made it this far before you died. That's it. That's all the information you get. Sounds impossible to beat the game, right? It might be impossible for us, but for genetic algorithm, that's a different story. Imagine a classroom, 100 students, one test. Everyone gets the same exam, but here's the twist. Nobody studied. They're just guessing, randomly filling in answers. At the end, obviously most of them fail. Now here's where it gets interesting. What if we took only the students who scored well, made them have kids, and those kids took the same test, and their kids, and then their kids, generation after generation. Eventually you will have a classroom full of geniuses without anyone ever opening a textbook. That's a genetic algorithm. So the wake flowchart for this algorithm is this. Step 1, create a bunch of random players. Step 2, test out those players. Step 3, give each player a score based on how well they did. In this case, score is based on how much distance they covered and how fast they finished the level. Step 4, next we need to choose which players will be the parents for the next generation, which is mostly based on the score of the players, and a bit of random mutation for the exploration of faster runs. Here's the final composition for the population selection. They are finalized after lots of trials and errors. 20% elite preservation, 60% crossover offsprings, 25% heavy mutation for exploration, and 15% random individuals. In simple words, players with a score of 2 will be selected twice as likely than the players with a score of 1. Once we have all the parents, we will make copies of them to fill out the next generation. And now if we run these guys again, it's not gonna achieve much because they are just perfect copies of previous generation. So they will do just as well as previous generation, which is not what we want. We want them to improve. So that's why we have the important step called mutation and crossover. This is where we make small changes to the player's brain so they act differently than their parents. Okay, next generation is done. Now we need to test them out. We are back into the testing phase of step 2 and bam, we just repeat the whole process. Test the players, evaluate the players with fitness function, select the parents which did the best, mutate their babies and repeat. Test, evaluate, select, mutate. Boom. That's an algorithm, baby. Let's go. Now an important thing, like I said, we make small changes to the player's brain, but I have not actually described what the brain is. Each player has a brain. It's no fancy neural network or anything like that. It's literally just a list of instructions which tells the player what to do. With instructions like stand still, walk right, jump right, run and jump, run left, walk left, etc. Each player follows their list step by step, and that's it. That's the brain. 100 Marios play the level. Most die immediately, but few, they accidentally survive a little longer. We take those winners, mutate their brains. So when we mutate the brain, we are simply just changing one of the instructions from jump to left or from right to do nothing. And this is how we create the next generation. Some of these mutations will make the players worse, but some of them will make them better. And that's the whole point of this algorithm. You repeat this 1000 times. You get an AI that beats the game without ever learning it in the traditional sense. It just evolved. And here's the crazy part.
These Marios can't even see the game. No enemies, no screen, no visible platform. They're just playing completely blind, guided by only one signal. How far did you get before you died? It's like throwing darts in the dark, but after throwing each dart, someone keeps whispering warmer, colder, warmer, and eventually bullseye. Now that we know how the genetic algorithm works, let's start the learning process and see our blind Marios evolve. At the start, they don't have any moves to work with, so they are just going right. At this stage, it's pure pandemonium. AI is pressing random buttons just to see what happens. Left, right, jump, crouch, all at once. No rhyme, no reason, just chaos. To gather experience and supercharged training process, we will have 10 Marios play 30 games simultaneously and each will play for one-handed moves. After the algorithm review all the players based on the scores, it will create the next generation. And if it goes well, we should see an incremental improvement and the whole process can repeat. After few iterations of training, AI survives noticeably longer than when its behavior was random. For some reason though, instead of going over the gap, it just keeps jumping into the gap and it becomes fixated on just jumping into the gap. Why is this? It turns out, when you're chasing rewards, it's easy to forget about the actual goal. See, the gap is actually a bottomless pit, and every inch Mario falls, that counts as distance traveled. So by our own fitness function, jumping into the pit is more rewarding than actually beating the level. And honestly, it hits a little too close to home. Think about it. How many times have you opened YouTube to watch one video and ended up doom scrolling for 2 hours chasing the next dopamine hit? We chase likes, notifications, small wins, anything that gives us a quick reward. And before we know it, we have fallen into our own bottomless pit, distracted from what actually matters. As humans, we can reflect on our behavior, but changing it, that's the hard part. For our AI though, it's just a few lines of code. Right now, our AI gets rewarded for total distance, including vertical. But what if we only rewarded forward progress? We tweak the reward function to only count horizontal distance and ignore the vertical fall into the pit. Note that each time we modify the rewards, we restart the AI training process, learning from scratch, because we want the full process to be reproducible. After this change, AI starts jumping over the pits on its own, and the AI starts to explore the world more. And with some more generations of training, it actually starts reaching the end of the level. Let's go! That was a time of 351, meaning our AI beat this level in under a minute. That's gotta be close to a world record or something, right? Let me check. Wait, what is this? That speedrunner is using the warp pipe. That's a shortcut? Wait, I didn't knew warp pipe saved this much time in this level. That's 369. They beat it even faster using the secret warp pipe. Alright, here's the thing. Our AI can't do that right now. I never gave it down as an input. So let's add the down button and encourage our AI to use the warp pipe by rewarding it bonus scores if it ever uses the warp pipe. Finally, it's working. We got our AI to actually use the warp pipe. But what was that? Did you guys notice? Somehow a random wall the size of a pipe just appeared out of nowhere. I believe that's an easy fix. Let me just delete these lines of code. Oh well, I remember now. Nothing ever works perfectly the first time or the second time. Oh well. Alright, let me spend probably like 6 hours bug fixing and we will resend it. Oh yeah, that sucked. But she's working now, so let's go. Finally, it's working. Skip most of the level and reach the end faster. But something still wasn't right despite making a lot of progress. As soon as our AI hits level 2, it starts dying immediately. This time making sure to get the jump time right and survival. And there was no way to recover from a mistimed jump like before. All that training from level 1 was basically useless here. This meant that at the end of our AI's best runs, there was a sudden and steep learning curve. It would need an insane amount of extra training just to survive the first few seconds of level 2. So we changed the approach. Train each level separately in parallel. Let the AI learn and adapt to each level on its own. We will be training all the levels of Super Mario Brothers simultaneously at once in parallel at the same time. So now we have separate AIs training on each level at the same time. So let's see how they are doing. First, World 1-1. This one is absolutely cracked. Our AI completes World 1-1 as fast as the actual human speedrun. This is genuinely insane. World 1-2 is where it gets really cool. Our AI doesn't just survive, it discovers shell surfing. It kicks a Koopa's shell and rides it, wiping out entire waves of enemies in one move. At the start, I would have never imagined our AI to find these kinds of cool tricks. Remember at the start of this video when I said our AI would do things that I never expected. This is one of those things. I didn't program that. I didn't even teach it that. It figured out the combo completely on its own through evolution. Now, World 1-3, this one's a completely different beast. I still get nightmares of this level. This level is mostly platforming that requires to jump on moving platforms with precise timing and very little room for errors while also avoiding flying Goombas. And for a blind AI, that's essentially getting every button right while also being lucky enough to catch a moving platform at the right time. That's the hardest kind of challenge. Our AI makes progress, but it doesn't fully crack this level. And honestly, I could have thrown more training time at it. Days, maybe weeks, or months even. But I had my eyes focused on a bigger prize. Because World 1-4 has Bowser and I had a promise to fulfill. It was time to get serious. It was World 1-4, the Bowser fight. This is it. This is what we have been building towards this entire video. Blind AI, no vision, no memory, just a list of buttons and one number. How far did you get? The first generation had to face a massacre. Hundreds of Marios just evaporating. They don't even make it past the fire bars. But generation after generation, they start getting further. Learning timing of fire bars, jumping over the lava pits. Our AI had no neural network, no deep learning, no billion-dollar GPU cluster, just Darwin's 200-year-old idea and a lot of dead Marios. We did it. We actually did it. From 100 random idiots smashing buttons in the dark with this. That's the power of evolution. That's genetic algorithm, baby. Let's go. Now we all know that genetic algorithm is simple, it's reliable, pretty much guarantees you will eventually get a player that can beat the level. And honestly, watching it learn looks really cool. But there's a fatal flaw hiding in the brain of this whole thing. The AI hasn't actually learned anything. Think about it. It has no idea where the enemies are. It doesn't know what a pit looks like. It can't even see pipes, blocks, or any obstacles. Nothing. It's not thinking. It's memorizing. Oh, there's a pit in front of me. I should jump. It's going, oh, my 67th instruction says jump, so I jump. That's it. That's the entire brain. And that means if we change anything, even something tiny, the whole thing falls apart. If I move my Mario's starting position just by a few pixels to the left, then it falls apart. Watch, all the jump timings are instantly off because it's assuming the pipes are going to be there. It either dies in places it used to clear perfectly or gets stuck in dumb spots. So yeah, we have beaten Bowser, but we didn't build intelligence. We build a really elaborate tape recorder, and that's cool, but we can do way better. It's time to bring in the big guns. It's time for... What if, instead of an AI that memorizes jump at frame 67, it knew there is a pit 3 blocks ahead? What if instead of a list, each Mario had a brain that could process the information and make decisions based on it? And that changed everything. And this time, it took at least 33,000 Marios dying before one of them figured it out. NEAT stands for Neuroevolution of Augmenting Topologies. Anyways, NEAT is also a genetic algorithm, but with neural networks. Look, neuroevolution is just a fancy way of saying genetic algorithm. Remember how genetic algorithm was just a list of instructions. Press A at frame 12, press right at frame 30, jump at frame 67. NEAT throws that entire system in the trash. Instead of a list of buttons, this time we will build an actual brain. Our AI will use something called an artificial neural network to make decisions. Basically, it's a mathematically modeled brain which roughly models how a human brain works. Every 10th of a second, this brain will get an input which describes what is actually happening in the game. In response, after thinking and processing, it will output a decision specifying the actions to be taken. A better trained neural network will be able to make decisions that ensures the AI will survive and finish the level as soon as possible. But this will only happen if the neural network is configured correctly. But that's the tricky part. To configure the neural network, we will be using genetic algorithm again. So like the previous algorithm, we will be utilizing evolution. Same training method, create a population, test them, keep the best one, mutate and repeat. But this time, we are using it to train a neural network instead of a list of button presses. So in this game, the inputs that our neural network will receive are the X and Y position of the player, whether or not the player is actually touching the ground, how much far the nearest enemy is, how much far away the nearest pit is, the horizontal and vertical speed of the player, and finally I have casted 8 different rays from the player to detect the nearest wall or obstacles. The actions that our AI can decide based on the inputs are jump, sprint, move right, move left and idle. So here are our final inputs and outputs we will be using. As you can see, the inputs are directly influencing the output of the network through a network of hidden nodes that do all the calculations and processing. So here is how the networks work. It is based on interconnected nodes which are connected in a linear fashion. Networks are made up of 3 types of nodes: inputs whose values are provided by the environment, hidden nodes which process the input, and outputs whose values are the actions taken by the AI. Next, we set the value of input with the help of the environment and following the topological hierarchy one after the other until we reach the output nodes. For each neuron, there are 3 operations to perform. Add the bias to the current sum, apply the activation function, and pass the output to the next neuron by multiplying it with the weight of the connection, and finally add the sum to the destination neuron. But here is what makes NEAT different from every other neural network. It is the augmented topologies. Augmented topologies means that the structure of the neural network can evolve over time. See, normally when people build neural networks, they decide the shape up front. I want 3 layers, 128 neurons each, these connections. It is all designed by a human, but NEAT says, nah, let evolution figure it out. It starts with the simplest possible brain, literally just the inputs wired directly to the outputs. No hidden layers, no complexity, basically a goldfish. And then it evolves. Every generation, mutations don't just change the weight of connections, they can add a brand new neuron where there was not one before, create a new connection between neurons that were not linked, remove connections that are not helping. The brain grows itself. Generation 1, a potato. Generation 50 is starting to look like an actual network. Generation 200, this thing has built a brain that a human engineer would have spent weeks designing. And the best part, it only adds complexity when it helps. If a simpler brain can solve the problem, it keep it simple. No wasted neurons, no bloat. But wait, how does the AI know what to do? We just give it goals and let it figure out the rest. For our AI to get any useful feedbacks, we need a gentle curriculum of rewards which will guide it towards learning the difficult objectives. The harder the goal, the bigger the reward. Perhaps the most basic objective to start with is to explore the level and cover the most possible distance without dying. We can use a simple reward function to reward the AI for covering most distance by rewarding the neural network 1 point for 1 in-game unit it travels in the level. Next, we can reward our AI for finding secret warp pipes, which acts as a shortcut to the end of the level. And finally, we can reward our AI for clearing the level, which is the final objective. But before we start training the AI, I have to show you how I made my own version of Super Mario Bros. The genetic algorithm worked on the emulator because it only needed one thing: distance. But for NEAT and PPO, our AI needs to actually see the game. It needs to know where the enemies are, where the bits are, how fast things are moving, and to get that information we need full control over the game code. We had a player controller that worked as a base Mario player. Now we just have to add Mario sprites to each of the states of the player controller: idle state, jump state, run state, and death state. That's it. And now we will do the same for enemies: walk state, death state, and all of it. And now we have to make the famous Mario level, World 1-1, floor placement, montage time. That's Unity, brother. Let's go. Easy. Okay, sweet. It does work. And now I could get the brick textures from the internet and add ground tiles to all the positions. Make sure each pixel lines up and then do that for all the pipes, cushion blocks, and so on. Or I could just get a screenshot of the game, edit out all the characters, and set the floors to be invisible. And boom, that's it. It's done now. Prepare to have your childhood immersion ruined in the best way possible. You know, in the original game, the enemies are spawned when they enter the camera view. And when they go off screen to the left, they are destroyed by the game to save memory. Also, they move in a straight line until they hit a wall or other enemies, and then they turn around and move in opposite direction. And if there is a pit in front of them, they just fall into it. In our case, I have scripted the same behavior for our enemies too, except for the spawn and despawn logic, as we want to train more than 1000 AIs at a time. So we need to get creative with how we handle the enemy spawn and despawn logic. So we will use a technique called object pooling to create a pre-initialized pool of enemies rather than frequently creating and destroying them. This will help us show the whole level with all the 1000 Marios on the screen at once with all the enemies and obstacles. But this creates another problem. In the original game, the 2 Goombas here are spawned when they enter the camera view, and they move until they reach a pit and fall into it. But in our case, this will create a parity for our AI. They don't get to interact with them once they fall off. To fix this, I took inspiration from Groundhog Day and The Edge of Tomorrow by making the enemies live in a constant loop. They spawn here, get destroyed when they fall off, and then they respawn here again, and the cycle continues. Next, we will do the same for all the other enemies too, as we don't want any enemies reaching places they are not supposed to reach. One more thing, because I value your time and also want you to see the progress of multiple generations at once, so I just overlaid the footage of multiple generations on top of each other, all interacting and playing the game in their own timeline, while also being oblivious and unaffected by other generations. With this, our Mario game is ready. And now, let's start training the AI. Generation 1, 20 Marios spawn. They all mash random buttons. They all die. Generation 2, same thing. Generation 3, same thing. Generation 4. One of them accidentally holds right for slightly longer. It travels a few extra pixels before dying. That's Generation 4's greatest achievement. But here's the thing, that Mario survived, it got copied, it got mutated, its children entered the next generation with a head start, and that head start is everything. By Generation 100, fitness climbed to 10.56. Some Marios were consistently clearing the first section. Not impressive, but alive. Now comes the part that made this video a total nightmare. Generation 200, fitness 10.60. Generation 500, fitness 10.70. Generation 700, fitness 10.75. Generation 1000, fitness 10.80. 900 generations of training, multiple days of training AIs. After 18,000 Mario, that's over 70 hours of simulated gameplay, and the fitness moved by 0.24 points. I looked at this screen for longer than I had liked to admit. I checked the console logs. I restarted the training. I tweaked the mutation rates. Nothing worked. The fitness was stuck. At this point, I genuinely thought architecture 15 inputs, 128 hidden nodes, and 3 outputs just didn't have enough brain power to solve this level. Was I not smart enough after all? Morale was low and I had hit rock bottom. Do I have to end this video right here, right now? Was all hope lost? But then, I did not want to lose hope and kept training the AI nevertheless. Fitness at generation 1480 was 107.12. Wait, what? Did we just cross the 4th pipe? 107 from 10 in the span of maybe 50 to 80 generations. The AI went from barely surviving the first section to clearing almost the entire level. At this point in training, for some reason, all the enemies of the central star block got bugged and created this bizarre, impossible wall of enemies here. And that's why for future runs, I implemented the Hedgehog Day inspired expected position looping for these enemies too. For now, it is good enough to train our AIs, as I am not expecting them to reach that far, cause they will need a lot of training time to do that. So for now, they are not supposed to cross anyway. Whoa! This AI agent just beat the impossible odds and crossed the impossible wall of enemies. I am proud of our AI agents. They did the impossible. Nice. They're definitely not supposed to do that. That's not what a human can do. This AI even did that move again and again. So let me implement the loop and we will resend it. They even started to find and use the secret warp pipes. Just after that, without much effort or training time, they started clearing the level 2. Now that it had completed the level, I was trying to train it to be faster and faster by giving a small amount of time for our AI agents to train and try to reach the flag faster. Giving them smaller chunks of time forced our AI agents to train and aim to reach further distance in least amount of time. And then the best brain ever produced, fitness 135.70. It didn't just reach them, it ran past it. So how does the brain actually work? Every frame, 30 times per second, the brain runs this calculation. The 8 input signals enter the left side. Each one gets multiplied by 128 different weights. In this artificial neural network, each hidden neuron represents something. We don't know what exactly. The AI didn't label its own neurons. But somewhere in those 2435 values, there's a combination that says when velocity is low and you're on the ground, there is no wall ahead. Press right. Say the grounded input is on and the velocity is low. The grounded signal hits hidden neuron 1 and gets multiplied. Each hidden neuron adds up all its incoming signal, it squishes them through a fraction and passes the result to the output. If the jump output gets a signal above the threshold, the AI jumps. Every single frame, input, multiply, squish, multiply, output. That's a thought, or at least the closest thing that an artificial intelligence can achieve. These are not the instructions I programmed. These are behaviors that evolved from nothing. From 33,000 dead Marios. That's how my version of neat algorithm worked. But the brain is tiny, 2435 parameters. It works for one level. But can we do better? Can we do it faster? Enter. Okay, I will be completely honest here. I don't fully understand how this works on a mathematical level. I have tried to research it, but the explanation looks something like this. And you know, life is just too short to understand letters wearing little heads. But here's the thing, I don't need to understand every equation to use it because other people have sacrificed their social lives understanding this stuff. And that's the beauty of open source. Everything we have done so far, genetic algorithm, need, they all use evolution. PPO says, nah, screw all that. Instead, we are gonna train one brain and we are gonna train it the same way that you had trained a dog. Except this dog has 100,000 neurons and no concept of traits. To configure this massive neural network, we will be using a method called reinforcement learning. With need, the brain evolved its own structure. PPO doesn't do that. We design the brain upfront, but the trade-off is worth it. A fixed architecture can handle far more inputs. This time, our Mario agents can perceive the game almost like a human would. One more thing, we need to define the size of the brain. Make it big? Fair enough. Let me explain why this is actually massive compared to what we have done before. Genetic algorithm was blind, can't see enemies, just memorizes button presses. Then we created Need, could see, had a real brain, but the brain was tiny. It was like a goldfish with ambition. It can handle simple tasks, but throw anything complex at it and it folds. But PPO, this bad boy can run neural networks the size of a building. We are talking layers upon layers of neurons, thousands of connections, kind of a brain that gives genetic algorithm and Need a generational or a minus. But the biggest difference is no more generation, no more populations, no more waiting for evolutions to figure it out over thousands of generations. Instead, we run 100 Marios at the same times, all sharing one brain. Think of it like a hive mind. Each Mario is out in the field gathering experience and they are all feeding this experience back to one central brain. The brain updates itself, learns from all of them simultaneously and controls all 100 Marios with the updated intelligence. It's like if you could clone yourself 100 times and send all your clones out to try different things and then absorb all of their memories at once. That's PPO. Before we send it, we need to define the inputs and the reward function. Need had 14 inputs. PPO, we are giving it 26. The additional 18 inputs are 8 raycast, nearest 5 enemies, distance to goal, is near pipe, is near pit. And for the rewards, we will be rewarding our AI for moving right with a small dopamine hit, getting closer to the goal, medium dopamine, for reaching a new personal best distance, bigger dopamine, using a warp pipe, you beautiful bastard, take lots of dopamine, reaching the flag, maximum dopamine. Actions that will incur penalties are standing still, moving backwards, jumping without going anywhere, and running out of time, dying. There are 11 reward signals in total, and even more that were tested but not ultimately used. And yeah, there's so much more I could be talking about: hyperparameters, learning rates, entropy's coefficients, but that will do. You get the gist. Alright then, let's send it. We have got 100 players running around at the same time. They all share the same brain, remember hive mind situation. So all these boys are gathering experiences and sending them home to one single brain. With each new attempt, the AI gathers data and uses it to tweak its brain, reinforcing actions that led to rewards, discouraging actions that led to punishment. Attempt after attempt, it gets a little bit better, and the PPO algorithm is what handles the actual brain surgery, something to do with proximal policies and clipped surrogate objectives, and a bunch of letters wearing little heads. But the point is, it works. The brain adjusts itself, learns from its own experiences, and gets better over time. After 5 minutes of training, and I mean real world minutes, not generations, because there are no generations in PPO, some of them starts figuring things out. They figure out that right equals good. Moving to the right makes the dopamine number go up, and the dopamine number going up is basically the meaning of life for these things. By 10 minutes, a few of them figured out jumping. Not just random jumping, they are jumping because there is something in front of them every few seconds. This loading screen here is what saves the memories of all the Marios to the single hive mind. But I want you to see the training process uninterrupted, so I will cut those loading screens out with the magic of editing. So here is something cool. We will show more than 1200 iterations of training in a single gameplay footage. This way we can visualize how the AI's behavior changed over the course of its training. The early iterations are shown in blue, the middle in green, and the later ones in red. Here we can clearly see that in the middle of its training, the AI was taking one path to the starting section, but later it switched to a different one, avoiding the center block, using the warp pipe to dodge the wall of enemies, and crossing the level while avoiding Goombas as much as possible. Now comes the part where things get interesting or frustrating, depending on whether you're watching or whether you're the one staring at the training matrix at 3 AM in the morning. It probably looks like my first attempt at running this algorithm, but it is closer to my fourth. If there is no progress at the start of the level, even after hours of training, our PPO is not set up correctly. And here's the thing about PPO that makes it both amazing and infuriating. You can't just wait. With genetic algorithm and need, you could go to bed and you wake up, maybe it figured something out overnight. With PPO, if it's not learning, you need to change something. The learning rates, the brain size, something. So here are the things that I tried. More enemies in the input, fewer enemies in the input, higher learning rate, lower learning rate, bigger neural networks, smaller neural networks, higher reward for jumping over enemies, penalty for standing still, penalty for going left, running more Mario agents simultaneously, running fewer Mario agents simultaneously, changing the entropy coefficient, and each experiments take about an hour. So yeah, I tried my best. But after my fourth attempt, something clicked. The Mario agents started getting past the hard section. Not all of them, but enough of them are feeding back good experiences that the brain starts to figure it out. And after about 7 hours of total training time on my fourth attempt, we have got Marios that can pretty consistently beat World 1-1. And here, watch it see the pit coming and it jump early. Not because frame 134 says jump, because it feels the ground disappearing under its feet through the recast and it decides to jump. PPO did it in less than 7 hours. Let us put that in perspective. After getting configured correctly, Knee took 276 hours, but PPO did it in less than 7 hours on the same level in the same custom built game. That is what happens when you give an AI a brain 53 times bigger and let it learn from its own experiences instead of waiting for evolution. Remember, we started this video with a square and a rectangle, and now we ended up here. 3 different ways to teach a machine to play a game, each one more powerful than the last, each one on a different philosophy on what learning even means. Is it memorizing the perfect sequence of buttons? Is it evolving a brain from nothing?
Is it learning from your own mistakes, one reward and punishment at a time? Honestly, it's all three. They all have their place, and that's what makes AI so fascinating. Hey, if you made it this far, you are genuinely my favorite people on the internet right now. This video took me an absurd amount of time between building the game from scratch, training 3 separate AIs, bug fixing at 3 am, and writing a script that somehow makes proximal policy optimization entertaining. So if you enjoyed this, if it made you laugh or think, wait, that's actually kinda cool, hit that like button. YouTube algorithm is basically its own AI, and the more you interact with this video, the more YouTube's AI will show it to other people who might enjoy it too. And if you want to see more stuff like this, subscribe and hit that bell so you don't miss the next one. I have got more AI experiments and more 3am debugging sessions coming. I have officially launched the Coding Kitty Patreon. It is the best way to support the channel, and as a thank you, I have uploaded the source files for the Unity and Gym Super Mario Emulator projects over there. You will also get the instructions to train the exact genetic algorithm and PPO models that we built today, so you can try it yourself. Even if you guys just drop a like or a comment, it will completely make my day and help me keep making these videos. But that's just an AI, a Mario AI.